I'm going to talk about object lifetimes. I originally titled the slide A Complete Guide to C++ Object Lifetimes, but then I thought this might be a bit too ambitious, so I got some insurance there. And as it turned out, because this was one of the talks where I I wanted to learn about it, so I submitted a talk. So when I wrote the outline of the talk, I didn't know the details. And the more I learned about it, the more I realized how incomplete this really is, and crucially, how many bugs there are in the standard about this. So we're going to see that. So it's about object lifetimes. So the obvious question is, what are objects and what are lifetimes? Now, I'm not meaning object in the sense of object-oriented programming, right? An object is a term of art from the C++ standard, and essentially objects are fundamental. Everything you do, you create, destroy, refer to, access, and manipulate objects in a C++ program. That's essentially all you do. And so to understand objects, we need to understand three things: storage, value, and type. So let's begin with storage. So the fundamental storage unit in C++ is a byte. So we've got a memory in a C++ program, and it consists of a sequence of contiguous bytes, and every byte has a unique address. So this is computer memory, and we've got some bytes, and the bytes store a couple of bits. And I've highlighted one of those bytes there. It stores the bits 0x42. Now the question is, what does this mean, right? And this is about the value. So what does 0x42 mean? It could be the 8-bit integer 65. It could be the character uppercase A. It could be the start of the string that begins with A. It could be part of the 32-bit integer, just like the first byte, and then we've got more of them, or whatever else, like some sort of enum. What does this mean? And so elements of programming makes a distinction between datums, which are just sequences of zeros and one, and then the datum together with an interpretation is a value. So we've got our bits, and when we interpret them in a particular way, this creates the value stored of those bits.
So this is a definition you're creating, or is this something you're referring to?
This is the term value is defined in elements of programming.
Oh, okay.
The standard doesn't really define it in this sense. It just makes more sense to understand phrases in that way. So, and now a type. Well, a type is simply describes the interpretation of a datum. So a type is essentially a mapping of bits to their interpretation. So for example, we can have the type unsigned char, which is 1 byte of memory, and we interpret it directly as an 8-bit unsigned char integer, unsigned integer. Or we could have an int where we take 4 bytes and we interpret them as a signed 32-bit 2's complement integer. A std string is more complex, so we've got 24 bytes and the first 8, then we've got a pointer to some other memory and so on. So a type just describes how to interpret the data. And now an object, informally an object has a particular type, occupies a particular region of storage at a particular address, and stores a value. So here we've got a bunch of objects. So we've got an object x, has type int, stores the value 42. Then we've got an object y of type float, stores the value of 3.14. And then we're changing the value stored in the object x with this assignment, and now it stores 11. So that is an object, right? It's something, it has a memory address where it stores a value, and that value is defined by its type and the datum stored at that address. So those are objects. Crucially, two things aren't objects. First of all, functions. So functions themselves aren't objects. They might occupy physical storage in your computer, but they are not considered objects. A function pointer, however, is an object. And a function implicitly converts to a function pointer to itself, which is a value, which can then be stored in an object. So, but the function on its own isn't an object.
But the standard library says is object on a pointer is false.
No, on a pointer is an object.
Okay.
Yeah. A function isn't. Also references. References aren't objects themselves, they're simply aliases to objects. So we've got our object x, and then we've got an alias to that object, which is a reference, which is simply another name for that same object. So naturally, all the properties that apply to the original object also apply to that reference, and it doesn't really matter what we use to refer to that object. They're aliases, they're identical. Now, what is lifetime? The lifetime of an object is simply a runtime property of an object. So if you've got our objects, they have a bunch of properties like the type, and the lifetime is another property of this object. And it's a pretty important property, right? Because all other properties of an object are only really valid through the lifetime. And in particular, before the lifetime of an object starts or after the lifetime has ended, there are significant restrictions on how you're allowed to use that object. So lifetime is a pretty essential property. And in a nutshell, the sort of life cycle of an object is as follows. So we first allocate storage, because we need a place to put our object. We then initialize an object. I put it in quotes because we will see later. And this starts the lifetime. So now we've got an object that lives at that storage. We can then use that object. We can read its value, we can change its value, we can do whatever we want with it. Eventually, we will destroy that object. This ends the lifetime. And then we deallocate the storage. And this is, in a nutshell, what every object goes through. And like all the interesting part is in the details, like when exactly does the lifetime start, when does it end, when is the storage allocated. Now, a note about terminology. In the standards, this says that objects can be created. This does not mean that their lifetime starts. It simply means that now we've got a thing with a bunch of properties that we can talk about. However, the standard also says that objects can be destroyed, and this is actually an operation you do in an object, and this actually ends the lifetime. Yes?
So in this case, then, would created be analogous to like storage allocation?
No, created just means we've got this thing now. We can talk about it later.
So it's not even guaranteed that storage has been
No,
allocated.
it's just like we've got an object that we can talk about, and then we can...
There's
a name for it.
initialization might have started
Yeah.
but not completed, for example.
Not even that, it's just like an object is a thing that we want to talk, like an object sort of exists after it has been destroyed. It's in a destroyed state.
You've
right?
allocated an identifier.
I've allocated an identifier for something, I've given something a name so we can talk about it.
Okay.
Right?
Got it.
Yes.
Do you have like a simple example of an object that's created but whose lifetime hasn't started?
Yeah, a simple example would be global variable initialization, thread local variable initialization. You have a thread local variable and you haven't started the thread yet. Right?
The object's been created?
Yes, because you've got the declaration that creates one. Like you can talk about it. Like it's not, the creation isn't a one-time thing. This isn't a one-time
It's a
operation.
logical property.
It's just like we want to talk about something.
Abstractly.
Like, yeah, like we declare an object, essentially. Right? And then eventually, like, once we do that, we can allocate storage for it, we can start its lifetime. But it doesn't, like, object creation doesn't map to any one-time operation. It's just that we've got an object. Right, you can talk about, so for example, consider a function local static.
Sorry, it seems to me you're talking about variables, not about objects. That's why I'm confused.
Well, variables create objects.
Like the variable might exist, but it might not, the object it refers to might not have been created. And is that what you're saying?
Yeah, no, the variable exists and the object exists, but the lifetime might not have started yet. Its storage might not have been allocated yet. We haven't reached the point where we did anything with it.
I like the thread local static.
Yeah,
example.
yeah. Like you've got a function local static written in your source code. Like you can talk about it. But before you call that function, like nothing at runtime, right?
Let's keep going. I'm not.
Yeah, yeah. Like it's a subtle distinction that isn't really important. I just wanted to point it out. Also, lifetime is something the abstract machine invented. Like it has nothing to do with the physical CPU. It's just something that we talk about in the standard to describe properties of objects. It's not a real property of anything actually going on. Like all of this is just standardese. Like I'm talking about details on the abstract machine and nothing on the physical CPU. So let's begin. This talk is structured in levels. We're going to go deeper and deeper, but let's begin with the simplest one, variable declaration. So this is a sentence from the standard that we're going to see a lot, various parts of. So the standard says an object is created by definition. And this just means that when we, for example, here we've got a variable definition, this creates an object. At runtime, right, we allocate the storage and the lifetime once control flow reaches that, but like we can start talking about X because it's there, it's been created by this piece of code, right? Then we can use it, and then we end the lifetime and deallocate the storage. So let's look at the rules and when exactly we allocate the storage and the lifetime and so on in more detail. And for that, we first need to look at storage duration. So the storage duration is the property of an object that sort of defines the minimum potential lifetime containing the object. And it depends on how we created that object. So here, and for this level, we only care about static thread and automatic storage duration because that's the one of declarations. So automatic storage duration is the easiest one. When you've got a variable in a block or parameter scope, without any special keywords, it has automatic storage duration. and the storage like lasts until the block exits. So when we reach controller, we allocate storage for those local variables. Then we allocate more storage. We deallocate storage of C because we end the block. And then we deallocate storage of A and B. Right? This is automatic storage duration. Static storage duration happens when you've got variable names in the scope or static or extern, and they live throughout the duration of the program. So here we've got a bunch of variables with static storage duration, and as soon as the program starts, we've got storage for them. Like immediately they're allocated, and there's only deallocated when the program ends. Thread storage duration is like static storage duration. You've got thread local, but then you've got like duplicate copies per thread, and the storage is allocated when we create that thread. So here, when the program starts, we create like one copy of the thread local variable for the main thread. And when we start another thread, we allocate more storage for that, for a distinct copy in that thread. And then when the thread exits, we deallocate the storage. Yes?
Is it considered allocated? Like my experience is like, thread locals aren't initialized before.
I'm talking about the storage allocation.
Right.
I'm not talking about the lifetime.
Allocated then?
Yes.
So does it have to do the allocation?
I mean, under the as-if rule, it can do it whenever.
Oh, okay.
Right?
But it's considered allocated. Okay.
Yeah, yeah. Like on the abstract machine, we allocate storage
when
when
you
we.
make the thread stack, you
Yeah.
get storage for the
Yeah.
locals.
Nope.
Nope.
Not on Windows.
Oh, well.
Yeah.
Well.
Like, I'm not talking about any hardware. I'm
Yeah,
talking
yeah.
about the abstract machine that
Exactly.
allocates. Right. Like, it's also like we don't deallocate stack space in the middle of a function either, right? So like, I'm talking about storage duration, and the storage duration is not the same as the lifetime of an object, right? The storage duration has to outlive the lifetime of an object because otherwise it doesn't make sense, but it's not the same in general, right? The lifetime begins when we have both storage and we done an initialization. Then does the lifetime start. So when does this initialization happen? And it depends on the storage duration. So for automatic storage duration, they actually match. So when we allocate storage, we also start the lifetime. There are some terms and conditions that may apply. We talk about those later on. For static and thread storage duration, it's complicated. So we've got function local statics with this global scope. We've got const init and dynamic initialization. We've got nifty counters. I gave an entire 60-minute talk about just static initialization. You can watch that talk to learn the details. I'm not going to repeat them here. Just like it's complicated, they're going to be initialized at some point. And then we can use them. But another caveat, like in general, an object can have its lifetime start without a known value. So when we allocate storage for an object, and then the object has an indeterminate value, and if we don't do any initialization, for example, because our class, it's like an int or a class as a default constructor, then that retains an indeterminate value, and when we use it, we have undefined behavior. So this allocates storage and starts the lifetime because we don't do initialization. So the initialization is complete because we didn't do anything, right? So we have an indeterminate value. This is undefined behavior because we're using it without a value. Like we're evaluating an expression that results in an indeterminate value. So we have to assign it first and then it's okay. This is actually gonna change. Yes?
So here basically you allocated the storage, you initialize the object, except you initialize it with an indeterminate value. And so the lifetime has begun. And then if you use it, you're using an object that is within its lifetime.
Yes.
But that has an indeterminate
Exactly.
value, and that's why that's
Exactly. Because like the assignment is fine because we can use that object, it's within the lifetime. Right? It's just like the read produces an indeterminate value. And they're like produced by an evaluation. There is some stuff in there about the comma operator or the non-evaluated operand of a short circuiting, like something. So like actually, well, like when you want to get the value, then it really matters. But like the lifetime has started, so we're allowed to use it, just not read it yet.
The problem is the value, not the object.
Yes. Right. And so this is actually going to change in C++26 to erroneous instead of undefined behavior. So this is a new term, and essentially erroneous is what we wanted to have undefined behavior in many cases. So the compiler is not allowed to do anything. It's only allowed to like issue a diagnostic and terminate the execution. So this is a more tame form of undefined behavior that makes use of uninitialized memory a bit safer.
And we might change that again.
And we might change that again. All of this is subject, yes. I'm purposefully not mentioning which standard the rules apply to in most of the time, because they're constantly changing and in flux. Yes?
Yeah, when it says it's permitted to terminate the execution at an unspecified time, I
Yeah.
assume that includes just not doing
Yes.
it. Okay.
It's basically a license for memcopy to terminate after the last uninitialized read as
Yeah.
opposed to the first.
Yeah. Yes.
Might be a misunderstanding, but wasn't it already permitted to do that if it was undefined?
Yeah, but
Yes.
it was also permitted to do more.
Wait, so what
Permitted
is it
to
not
launch the
permitted?
missiles.
Right, but what is it not permitted to do now?
It can eliminate a branch based on the fact that this would produce undefined behavior. Right? It can no
So
longer
it
do
can't
that.
even like treat it as if it was 0 initially?
No.
No, you can't.
Things like it can't make optimizations based
Yeah.
on the fact that it's
Yeah.
undefined behavior.
I know, so
Undefined
you can't,
behavior.
like if you print an uninitialized int, it can't print 0, it has to like terminate?
No.
No.
That seems to be what you're saying here, right? You're saying you can't do anything other than those.
It is permitted. It's
Yeah.
not
But you're
required.
saying if it can do other things, it was already allowed to do other things. If it can't do other things, then it can't print 0.
So this is like the wording is like, this is not the wording, this is like the informal
Oh.
description, because the wording was like multiple
Okay, I
pages.
thought that was the wording.
No,
Okay,
no,
gotcha.
no.
Okay.
Sorry, I should have made that
The
clear.
paper is erroneous behavior for uninitialized reads by Thomas Köppe.
Yeah, it's a P2795. Yeah, so yes, like it's more tame form. This is not the wording. Sorry about that. Yes.
But what about all the optimizations that we miss?
Yeah.
Assuming undefined reads don't happen.
Yes, they don't happen anymore with that. Yeah.
You can turn it off. The paper describes a way to
Yeah.
default it
Yeah.
back to the old behavior if
Yeah.
that you're relying on that.
I actually have more interesting stuff to talk about. I mean, we can talk about variable declaration all day long. Okay, new and delete. An object is created by a new expression. And then we've got a corresponding delete expression, which destroys an object. Right? So, like very basic, new int creates an object and starts the lifetime because we allocated storage and we performed initialization. Yes?
Oh, so I just want to make sure that I'm understanding here, because we had said previously that created just meant that there was a name for it,
Yes.
like the source, essentially.
Yes.
So
Yeah.
would it be more accurate to say that like new begins the lifetime, like it allocates storage?
Yeah, so this phrase just the sentence just lists all the places where objects are created, and then the wording for new expression, which I haven't shown, like allocates
I see.
storage and
Okay.
performs initialization, which starts the lifetime based on the other wording. Right? So this just yeah. We can then use the object as before, and then we delete it, destroy it, end the lifetime. And not only like we're having two objects, we've got like the int on the heap, and then the pointer, which is another object with the rules from the previous name. And here we can also have the thing with indeterminate values, which can lead to undefined behavior unless we assign it as before. So that's actually easier. So let's talk about temporaries. So an object is created when a temporary object is created, which is a great tautology if you pick the quote apart like that. So for example, here we have a function that takes a reference, which needs to be an alias for an object, but we're calling it with 42, which isn't an object. Like it's the number 42. So we need to create an object to make it work. Yes. So?
I just said that 42 was a literal.
Yes. Yeah.
Not an
Yeah.
object.
It's not an
I'm
object.
agreeing with you.
Yeah.
So this is a great example of when we create an object without a storage for it yet, because a temporary is just hoisted to wherever it's gonna land magically because we've got copy elision. So when you create it, you actually don't know where the storage is. Really.
Yeah. But like we can start about this, we can talk about this temporary object that must exist somewhere for this code to make it.
Well, I mean, first it's a literal, then it's a value, and then it's an object.
Yeah. So the technical term for this is temporary materialization conversion, which is a great phrase for Hangman. And the description for it is like somebody was trying to hit the word count. So a PR value of type T can be converted to an X value of type T. This conversion initializes a temporary object of type T from the PR value by evaluating the PR value with the temporary object as its result object and produces an X value denoting the temporary object.
Thank you, Jens.
Yeah. We're going to create an object initialized by the PR value there. Right? And this happens like whenever we use a PR value where we need like an R value reference, like an X value to something. Like binding reference to a PR value. So this has to be a const L value or an R value reference, because on compilers, most of them, L-value reference but don't bind to PR values. When you do member access on a PR values, so you've got this pointer which needs a memory access, so we need to create an object in order to create a temporary out of it. When we use an array, arrays really like to be pointers, so we, like whenever we use an array PR value, we create an object to make it work. And this is interesting when we discard the result of a function call that returns a PR value. So consider a function that returns a std string by value. The result of this function call is a PR value. But we want to destroy the string to free its memory, so we need to call the destructor, which requires an object. So we're creating an object from the PR value and then immediately destroying it, just in order to make the destructor call work. So what about the lifetime of a temporary? So when we create the temporary, we also start the lifetime, like when control flow reaches the thing. And this is not worded precisely. And then we destroy it, like when we last step of evaluating the full expression. So here we've got a function that takes a bunch of references, and we're calling it with 2 PR values. So we need to create 2 temporary objects. There's have to be like the lifetime starts sometime before we call the function, and then destroy it at the semicolon. So after we're done with the function call, we destroy the objects. And this means it's safe to use them within the function, right? Otherwise, it would be quite silly if we create the object, immediately destroy it, and then we just have a dangling reference. Like then it would be better to not compile. Yes?
If I remember correctly, I think evaluation order for function arguments isn't guaranteed.
Yeah.
Is there any actual guarantee as to what order those objects are destroyed in or initialized?
In reverse order.
Well, yeah, but I mean, is there any reverse order of whatever was
Yes.
actually done?
Yeah.
But is there any guarantee of what will be done?
No.
Yes. Okay.
It's very important that there isn't.
So there are
Also, unless you're in arranged for loop.
exceptions. This is called temporary lifetime extension. So the first thing is when you bind a reference to a temporary, the lifetime of the temporary is extended to match the lifetime of the reference. So here we're creating a temporary to bind the reference. And with the previous rule, it would be immediately destroyed at the semicolon, which would be silly, right? So the lifetime is extended to match the lifetime of the reference. Like I haven't introduced lifetime of references because they are not objects, right? But like the lifetime of the reference is as if it was an object. So in this case, when the closing brace of the thing, we destroy the temporary only when we reach the end. So this code is fine. It's really subtle, however, because it only happens when we bind directly to a temporary. So here we have a vector, they return a vector of strings. So in the first case, we've got temporary lifetime extension because we bind a reference to a temporary, to a PR value. But then in the second case, we're calling square bracket operator, which returns a reference. So we're not binding a reference to a PR value, we're binding a reference to a reference. So we create a temporary object to call the square bracket operator, then return a reference. That reference is bound to the other reference. But when we reach the semicolon, we destroy the temporary object we've created, right? And immediately have a dangling reference. So temporary lifetime extension for variables isn't really nice. The second exception is for functions, for range-based for loop. So all temporaries created within the range expression, so after the colon, are destroyed only at the end of the loop. So this code is perfectly fine, because the temporary we create to iterate over it is destroyed at the end of the loop. But so is this one, because the temporary we created to call the square bracket operator is also destroyed at the end of the loop.
Thank you, Nico.
Yeah, thank you, Nico. This was a recent change to make this one work. Before that, only the first case would be okay, because then we actually have a reference to a temporary internally. And the second one would be dangle, but no, both are fine because we artificially extended the lifetime.
Did that happen in 20 or 23?
23. Yeah. Yes.
And that's true for like any number of temporary things.
Any number of temporaries in the range-based for loop.
Okay.
Yeah. And it's like the only thing where this behaves like that. Yes.
Why was a special case here for the for
Read the paper
Yeah.
and about 1,500 different email threads.
Yeah. It was very easy to write buggy code with ranges.
Okay, makes sense.
It's still easy, but not here. Yes.
Is the same thing true for if or not? Like,
No.
no.
Only for 4. You wanted? No. Okay. Okay. So let's talk about the actual interesting stuff. Placement new. So again, like an object is created by new expression, but there's a special kind of new expression, placement new, which is essentially an explicit constructor. So we've got some memory, we can explicitly create an object in that memory. And you have to be a bit careful because placement new can be overloaded. Like essentially you can have a new expression that takes arbitrary arguments and do whatever. So when you want to actually call the placement new that you want, you have to use like double colons to create in the global scope and then static cast it to void. Because it can be like, there can be you can write an overload that takes an int pointer and do whatever, right? So you have to do it like that. There's also the standard library function constructors, which does that for you. 2 things to note. First of all, it's const expr. but placement new isn't. Except, for example, on Clang, placement new is constructors only if it's inside a function called std_construct_add. So this is literally the implementation of std_construct_add under Clang, which is like I wanted to avoid including memory where it's defined for some header. So I wrote my own overload of construct_add that takes like a special tag, so I can have like constructors placement new under Clang. But anyways, I'm not going to be using it in the slide code because it takes a t-pointer, and then in many cases I would have to reinterpret cast to a t-pointer, and I'd rather static cast to a void pointer. So I'm just going to stick with placement new.
Yeah. Now, if there's already an object at that start, you'll get to that.
Yeah, we get to that. Yeah. Okay.
Oh, wait. So I was going to say, the placement new in 26 will be constant square as well.
It depends on how much time Barry has.
I thought it passed the new.
Oh, okay. I don't know.
Yeah. Oh, I guess it didn't go
Has
through
it passed core?
Yeah.
Yeah,
Okay.
yeah. Okay, so we manually create an object, which means we also need to manually destroy one. Because the compiler doesn't help us, and for that we can explicitly call the destructor. That is the syntax, and the syntax is a bit weird because the T has to be like an identifier. It cannot be a keyword, so it cannot call placement new on an int, and it cannot be a namespace qualified name. You can still destroy those things, just not with the syntax. Like you have to use a type def to make it work, which is like bizarre and annoying. So I am actually going to use the standard library function destroy_add, which always works because here like T is an identifier. Even if like T actually is an int, it just works because like just the grammar doesn't allow an int in there, which is a bit odd. So we want to create an object in some memory. So how do we get memory without objects? Right? This is the question. So for example, malloc gives you storage. It doesn't give you objects. So then we can placement new to create an object and start its lifetime. We can then use it. We can then destroy it by ending the lifetime. And then we can deallocate the storage. And then we've got like the object lifecycle completely explicit. We've done every single thing. Similarly, we've got operator new, which is the C++ version of malloc. So this is not new. It just allocates memory. It doesn't create objects. But same deal. We can call placement new, use it, destroy it, deallocate the storage. More interesting is when you've got an array of unsigned chars.byte. This allocates storage, in this case, suitably aligned and big enough for an int. Yes?
Can you go back to the previous slide? Are you allowed to operator delete PTR instead of memory?
Are you allowed to delete probably?
I don't think so.
So you have
So
to keep track of 2 pointers?
I'm going to talk about using pointers after an object has been destroyed later.
Yeah.
I think it's fine, but I have to look about what's on my slide.
You can't. Oh yeah,
Sorry,
you can't.
what's the issue?
You can't delete PTR because PTR is typed and memory isn't. So
I mean, it takes a void
Global
pointer.
operator delete.
Yeah, it takes a void pointer and then it's just a function.
Yeah.
Yeah, that takes a void pointer, so implicitly
but it
converts.
wouldn't destroy the int if you just deleted it without destroying.
No, it just
Yeah,
deallocates the storage. It still does the
destroy
same
it.
thing. It's about whether you can write pointer instead of memory here.
Oh, so then never mind.
Yeah. So this allocates storage.
No, I don't think you can because that's zapped.
Yeah, I'm gonna talk about that. It's not zapped. Then we've got a buffer, and then we can explicitly start the lifetime of an object in there. Then we can use it. Then we can end the lifetime. And then the storage is deallocated because it's local. So I've made a special exception here for unsigned chars.byte because this just is special wording that they provide storage for objects. But we can also do something more interesting. We can reuse the memory of an existing object. So here we've got our int. We then destroy that int. So now we've got like a shell where there used to be an int. And then we call placement new. And now we've got another int at the same location where we previously had the int object, which we can then use because we've got an object. And then something interesting happens here. I'm going to talk about exactly what's going on, but this ends the lifetime of our int object. Which one is more about that later. So we can reuse the object, the existing memory. Yes?
Can you print X instead of the reference?
Can you print X? I will get to that. So you can do that, but you have to be really careful. For starters, const is const. You've got a constant, you end its lifetime, this is fine. You cannot call placement new on it. Because this would mean that we suddenly changed const memory. Right? This is undefined behavior. Const means const. Mostly. Because when it's a heap object, it's fine. like const on the heap doesn't matter.
You can go back one slide. So you're destroying x twice, right?
I mean, I already have UB here, so it doesn't matter.
Oh, okay, right.
Yeah. So const on the heap doesn't matter. The destructor still runs. So we've got a string, we destroy it, and then the compiler calls the destructor to destroy it again. Right? So when you've got the non-trivial destructor, the compiler will insert calls to that, so this will destroy the string twice, so we have to be careful and put something back in before that happens. Crucially, if the type doesn't have a destructor, like an int, the compiler actually doesn't call the destructor. More about that later. So this is the code that we have. We have an int, we destroy it, we create a new one, we use the pointer. Question in the back was, can we do that?
I don't think so.
For here, I think so.
And sorry, this was a rhetorical question. I know the answer. So we have to talk about transparent replacement of objects. So if after the lifetime of an object is ended, a new object is created, a pointer that pointed to the original object, a reference that referred to the original object, or the name will automatically refer to the new object if the original object is transparently replaceable by the new object. Another great sentence. I think it's one, yes.
It has to still be an int.
Yeah, so what does transparent replaceable means? The definition is complicated, but essentially A is transparently replaceable by B if A and B use the same storage, A and B have the same type, ignoring top-level CB qualifiers, and we don't have const objects, base classes, or non-unique address members. And then it's like when you have sub-object, it transitively goes to the parent one. But what this means in practice is that this code is fine, right? We do a transparent replacement of the int, so we can still use x, because it transparently got updated to refer to the new object. And similarly, we would be allowed to use any pointer or any reference to x.
Right. And the upshot of this from a compiler's point of view is that they can't put x in a register.
Yes, it can't put x in the register. Right. Yes. The compiler probably doesn't like what we're doing, but he has to support it. Similarly, this code is also fine. Right? We destroy it, and then we transparently replace it at the same address, at the same type. Everything just works fine. We can continue using it as if nothing happens. Yes?
Regarding to base classes, does this mean foo may not have any base class?
No, we cannot say
Only
foo, the base part of foo cannot be.
Only the base part
Yeah.
is allowed.
Yes.
I think so. You can't write that if, for example, foo is used anywhere with a new unique address attribute, for example.
Oh yeah, that could be the case. Yes, because we recursively go upwards. Yes.
So actually, like, if you do that and you happen to have trailing padding at the end of foo, what's going to happen is when you placement new in there, right? The compiler is actually free to override, like, is free to assume that you have size of foo bytes available.
Yes.
But there may actually be another object that's
Right.
using your trailing padding bytes because you're using no unique address
Yes.
attribute, and so you're actually going to be overwriting that
Yeah.
object that is hidden in your padding.
Yeah, that's a good, like when foo is not a complete object but a member of something else, like a sub-object, then the rules need to apply recursively to the true object. So the true object can't be a no unique address thing.
Yeah. Which is really, really tricky here, is that when you write your operator
Yes.
people, you have no idea, like, this looks correct, but it's
Yes.
not correct, it's made incorrect by the usage of it.
Yes.
via a new
Yes.
We
Yeah.
actually had an API break in the C++
Yeah.
in LVM 18. Because of
Yeah, I should have made it clear that I'm not recommending, right? But like the star this, for example. But yeah. Okay. Yeah. But very good point. Yes. Similar caveat here. When we do, like, depending on how foo is used, this might be problematic if it's part of a beer string. So we've got our const int. Remember, on the heap we can replace it, but this is non-transparent because it's a const object. So this is UB, right? Because the compiler assumed that pointer points to a const int, so this will never change. Then we change it, which is fine because const on the heap doesn't matter, but the compiler still assumes that pointer, like star pointer, hasn't changed, so it's allowed to, like, print 11 instead of 42. How do we fix that? Say it with me. Launder.
You know what?
Yes?
Your slide would be even better if it had assert pointer equals new pointer, just to drive the point home that it's the magic.
I'm going to talk about
pointer.
Yes, I'm going to talk about the word I'm not saying right now later on.
Okay.
Yeah. Yeah.
Which const is the problem? Is it the left one or the right one?
This const.
Thank you.
Yeah. You can const cast it away, and then, like, but it's still undefined behavior. because the type of a pointer doesn't matter. More about that later. So the fix is launder. Launder is a magic identity function. It doesn't change the pointer, but it magically makes it okay. How exactly that's going on later on. Similarly, standard launder can help with references. So same deal, now we're just using references. Using the reference is UB, but we can launder it. You just have to take the address and then start, and then it's fine. However, standard launder does not prevent UB. So we're assuming float and int have the same size and alignment. We're creating a float. We're destroying that float. We are putting an int at that same address. This is non-transparent because int and float are different types. We can use the int pointer. We cannot use the float pointer. We don't have a float. Even if we launder it, we still don't have a float there, right? Still undefined behavior. Launder isn't magic and says now you be here anymore, right? It does a very particular thing. So when do you want to use the launder? Well, when you want to reuse the storage of const heap objects. Because remember, if you have a const non-heap object, you can't reuse the storage anyway. Only for const heap objects. Base classes honor unique address members. So in other words, never.
Is there like a particular reason that const is weird with the heap? I had never heard that before.
I don't know.
It's just historical, whatever.
Yeah, it's
Okay.
the standard says so.
Okay.
Yeah. And I want to point out when launder was first added, the rules were more strict. They got relaxed, and so we need launder in basically no cases when you write regular code anymore. The standard library implementers are looking at me funny. Okay. Questions about that? Okay. So let's talk about implicit object creation. Another great tautology from the standard: an object is created by an operation that implicitly creates objects. The intent is the following code. We're using malloc, like a C programmer would, and then we just start using it. This should not be undefined behavior. However, under all the rules we've discussed so far, this would be undefined behavior because we don't have an int. We've just allocated some storage. So how do we make this code well-formed? Because we want to make it well-formed. Like for a very long time, this was undefined behavior, according to the standard. But like nobody did anything about it because clearly this was intended to work, right? And then Richard Smith came and fixed it finally in C++20. So some operations are defined to implicitly create and start the lifetime of objects of implicit lifetime types if doing so would result in the program having defined behavior. So in other words, a very unique situation. If it helps you, the compiler creates objects for you. So like the compiler goes out of its way to prevent undefined behavior for you in this particular situation. Like usually the compiler does the opposite, but here the compiler helps you. It is nice. Yes?
I think the most interesting thing here, because I know memcopy is one of these things that can do it as well.
Spoiler,
like,
yes.
Yeah, in many cases, like it just creates whatever it needs to. Like
Spoiler.
Oh, sorry. Yeah.
So the equation for like it needs to be an implicit lifetime type. This is the formal definition, but like essentially the constructor and destructor need to do nothing, right? If they have side effects, the compiler cannot just silently ensure that those side effects happen. But for example, like an int, a trivial type, all of those are implicit lifetime types. The words work. So what operations implicitly create objects? Malloc, invariance, operator new, allocate, and other allocation function. So this code is fine because the malloc implicitly creates an int to make this well-formed. Similarly, whenever we have a lifetime of an unsigned.byte array, this implicitly creates an int. So we have a buffer. This implicitly creates an int because we need an int to make it well-formed. Except this is undefined behavior. Because of a bug in the standard, you need to std launder here. This is really bad for like pedagogical reasons. I want to talk about this later, but just to make like pretend the launder isn't there. We'll talk about it later, and it's my opinion that the launder shouldn't be there. This proposal fixes it. Like this is a bug in the standard. There's some missing wording to make it well-formed. Details later. Memcopy and memmove implicitly create an object. So this is a char buffer. Char is not unsigned char.byte, so this creates nothing. However, when we memcopy an int in there, we create an int. Because memcopy implicitly creates objects, and then again the launder, because of the bug in the standard, then we can use it and then it's fine. Yes?
How does it know it's creating just because of the size of int?
I will talk about it later.
So when is 3006 supposed to land?
It hasn't been discussed yet, but it was scheduled for Tokyo, but they didn't get to it. It's a brand new thing.
Okay.
And finally, like implementation-defined functions we can also, like for example, mmap would probably implicitly create objects just like malloc. It's not in the standard, but the implementation can extend the set to make this well-formed. So how does the compiler know what objects to create? Well, the answer is easy. It uses time travel. So here we've got a buffer. And then depending on where we roll the dice, and we either need an int or float. And so it's important, like the reinterpret cast doesn't create the object, the declaration above. So as soon as we reach one of those lines, the compiler travels back in time in order to put the int in there, because we need an int to make it well-formed, and then execution continues. Alternatively, we can think a bit of quantum mechanics, like the compiler creates both an int and a float in the buffer, and like as soon as you need one, it collapses. Yes?
What if the program terminates like in between? Then is object created or not?
If you don't like it's time travel. Like it looks like when you need an object, it travels back in time to create the objects. But if you terminate before you actually need the object, the compiler never travels back in time.
Do you have a cat or not?
Yeah, yeah. And like this is why the constructor doesn't have side effects, because I don't think time travel is implementable. Right?
Citation required.
Yeah, I'm not a compiler writer. Don't quote me on that, but I don't think otherwise it would be possible to do. Yes.
So in practice, are compilers actually doing this, or is this the abstract machine?
And this is for the abstract machine.
Okay.
Yes, yes.
So this is just logically.
This is logically to make like the compiler to implement that. The compiler didn't need to do anything.
This is a mechanism for making sure that the behavior is not undefined.
Yes, yes.
That's what it is.
This is a voodoo trick the standard committee Richard Smith came up with to make this well-formed. Like, no compiler.
It's only in your head, right?
Yes.
It's in the compiler.
Yes, yes. We're talking about the abstract machine here. Yeah. It's important to point out that, like, once we put an int or a float in the buffer, there's an int or float in the buffer. We can then not later change its mind and use it as the other one, right? Once we execute this line, there's an int in the buffer. There always has been an int in the buffer, and there's never going to be anything other than an int in that buffer, right? So you then can't use it as a float. And just like std launder, it does not prevent UB. Like we've got the int, we reinterpret cast to a float, and we use it as a float. This is still undefined behavior. We don't have a float. Like we don't implicitly create a float to make it well-formed, right? This is not a magic fix against all UB, only a very specific set of UB. So you're reading data from the network. You write code like this. You got some bytes from the network. You're doing reinterpret cast to get the data. You start using this. Depending on how you got the bytes, this might be undefined behavior, right? If they came from like a function that is like magically blessed to create objects for you, this is fine. But if they came from anything else, this might be undefined behavior. Like it depends on how you call it. So to fix it, we need some way to implicitly create objects at that place, right? You might think, okay, easy, we use placement new. Data is trivially constructible, so this doesn't do anything. Like no initialization is performed. However, placement new starts the lifetime of a new object. So any value that was there stored before might have changed semantically. Right? This is not guaranteed to print the data that was actually in there, because we create a new object, and the lifetime of the new object, like all the properties that apply to the previous object in there, no longer apply, including the value. So this might change the value, even though it doesn't change the value. But like this, it doesn't do what you want it to do.
No, it does change the value. It doesn't change the bytes.
Yeah, it changes the value. It doesn't do anything on the CPU level. But like semantically, it changes what's in there. Yeah.
UBSat is free to insert a pointing value in there.
Yeah, UBC can put whatever it wants inside the placement. For example, like a compiler flag that zero initializes everything, right? It's fine to run here. So the fix is to call std_start lifetime s. Start lifetime s is live placement new, but it really doesn't do anything. So we just say, this is a buffer, start the lifetime of a data object in there and give me a pointer. And then we can use it. Right? This is fine. Yes?
And if there already is an object logically there, it just doesn't do anything?
Yes.
Okay.
No?
Well, it's not wondering like that.
No, it just...
Yeah, so we're getting...
It doesn't actually run any code.
Yeah, so like semantically, we've got our bytes. If they came from a non-blessed source, we need start lifetime s to get a pointer to the data. If they came from something else, The start lifetime s doesn't mean we don't need to do the magic anymore, and like the compiler never time travels to create the objects.
Okay, yeah.
Right?
So like it's well defined in both cases, even if the thing was previously
I'm gonna have examples where something is in there and then we use start lifetime s.
I don't think you can start lifetime as on a way if you've already created an object.
I've got examples for that. I will come back to them.
So you're saying I can assemble the Frankenstein and that puts the lightning into it, but I can put lightning in it twice?
So formally, if there's no, I'm gonna talk.
Right.
Yeah. Yes.
Just what standard is it?
23. Yeah, but don't worry. I'm gonna show you an implementation of start lifetime s. So also an array overload to dynamically create on. This is an implementation of start lifetime s. We do a memmove of pointer to itself, because memmove like implicitly creates objects in the destination storage. So we're just copying the bytes to themselves, but also magically creating objects. And then we just need the launder because we don't know where the pointer came from. And,
Do we have constructs for mmove?
no, I don't think start lifetime s is constructor. Yeah, but like the standard library implementation uses like compiler magic that also works for const memory and whatnot. But like this is like an approximation of what it does.
This is a lot of dancing.
Yeah. So objects are also implicitly destroyed. So the lifetime object ends when either it's like destroyed or like when we release or reuse the storage. So this is what happens when we have like, for example, here. We've got our x, we call placement new on it. This reuses the same storage, so it implicitly ends the lifetime of the int. And then we've got a new thing, but because of transfer to placement, we can use it, right? And similarly, like because an int doesn't have a destructor, we don't actually call the destructor at the end of the function. We just release the storage, which just ends the lifetime automatically, right? And the similar thing happens, for example, here. We've got a buffer. This actually starts the lifetime of an unsigned char array, right? And when we placement new is, this ends the lifetime of the unsigned char array and starts the lifetime of an int. And similarly, when you have like something and then you call start lifetime as of an object, I'm answering your question. When you have got an int and you call start lifetime as on that int, you end the lifetime of the int that was in there and start the lifetime of a new one.
Oh, it automatically does that.
Yeah, because because you reuse the storage, right? Yeah. As a consequence, like memory leaks aren't undefined behavior. We've got a string, replacement new over it. This ends the lifetime of the string, starts the lifetime for a new one, and leaks memory. But this is fine. Right? It's just a memory leak. Okay. Any questions? Okay. So let's talk about provenance. I've got some code. I've got an x and a y. I set y to 11. I do something with the address of x. I return y. Right? The compiler optimizes that to return 11. Right? Because we don't touch y. But what if do something does this? And what if just so happens that like the address of x plus 1 is the address of y? Then this function changes y. Right? It's undefined behavior because like okay, so first of all, this might not guarantee to work, and it might be undefined behavior, and it's undefined behavior. So the compiler is still justified to do the optimization. But what then if I put this if in there? Like if the address of x plus 1 is the address of y, we do something with the address of x, which means this sets now y. Like whenever we execute do something, like this changes the physical address of y.
The comparison is ill-formed.
Yeah.
Now, and the comparison is defined. You can compare pointers with equals equals.
Only if they're
in the same allocation.
No, less than in the same allocation. Equals always. Yeah.
Otherwise, you'd never be able to check if two iterations are equal.
You're not allowed to read after that array with one int.
Yeah. So, but like it's the same address. So why am I not allowed to? Like the point is, this like we still want to do the optimization. So there has to be undefined behavior in there, right? And the reason there's undefined behaviors in there is just because two pointers are equal doesn't mean they point to the same object. Just because two pointers store the exact same bits and point to the same address doesn't mean they point to the same object, and you cannot use one in place of the other.
Suddenly we're back 12 slides.
Yes. But I wanted to build it up slowly.
I'm just saying.
Yeah.
That was the thing I commented about.
Yes, I know. I know, but yeah, I know. So logically, like a pointer is a pair. It has an address, which is the physical thing in memory, and it has a provenance. So the address is stored in memory, and it means what does the pointer point to, and then the provenance sort of identifies the object or the allocation the pointer points to. And so a pointer dereference is only valid if the address is in the range of the allowed addresses for that provenance, and the current provenance at that address matches the provenance of the pointer. And crucially, pointer arithmetic does not change provenance. So here, even though the address of x plus 1 and y might have the same address, they have different provenances. And this is UB because the provenance of x does not allow this dereference. Like, even though it's the same address as an object we're allowed to touch, like this is still undefined behavior because the provenance doesn't match. Yes?
But can you do address of x plus 1 because you're not pointing to an array? Can you do that?
Yeah, you can have the end pointer of everything. Like, yes?
If you think of x as a sequence of one element,
Yes.
you know,
Yeah.
You're allowed to take the address of one passed into the sequence.
Yes. Right? It's yeah. Mike.
So before, when we had this situation, we used launder, right? If you use launder here, is that also make it okay all of a sudden, or no?
I will talk about that.
Okay.
Yes?
What happens if you did pointer plus 2?
That would be undefined behavior.
already.
Yeah, yeah, and this x plus 2 would also be undefined behavior.
Yeah.
Because you're only allowed to go past 1, not past 2. Yes.
Even just forming the pointer, even if you don't do anything.
Yes, yes. Yeah. Yes.
So does this all fall out of the fact that there's no like type difference between a pointer that points to one element versus a pointer that points to an array of elements?
What do you mean? So provenance exists because the compilers really want to do this optimization. Right?
So getting back to the equals equal.
Yeah.
Is the compiler not allowed to just immediately put a false there because like they're just coming from different provenances? There's no way like numeric value doesn't matter. Right? The provenance.
No, like you could want to compare the bits of the pointer.
I think it can because I think that comparison, the result of that comparison is unspecified.
Yeah, that
undefined.
might be. Yeah, that
so
might be.
it can
yeah.
just just make it.
Yeah,
up.
yeah, that might be. Yeah. Yes.
So you said just because two pointers have the same bit pattern doesn't mean they point to the same object. That seems like a heavy hammer for allowing this optimization. You could just say they point to the same object, but you're still not allowed to use it. Like, so why didn't they do that?
I mean, what do you mean by you're not allowed to use that?
Like the provenance, you can say provenance still matters even if they point to the same object. You still have to derive the pointer correctly, right?
Yeah, you have to derive the pointer correctly, and provenance exactly tracks where you derived it from. That is what provenance is.
I get that. What I'm saying is the notion of they don't point to the same object seems like a heavier notion than this. Like, do you need that for some other reason?
I mean, it points to the same object just means you cannot dereference it, right? Because it's not derived from the same source. Like, I don't know what you want me to say to make this less heavy.
Okay, I guess here's another question. Does it have other implications besides this?
Yeah, for example, this one. We create a constant object in the heap. This is provenance A. We destroy it. We replace it. This creates a new object with provenance B. We're allowed to use the new pointer. We're not allowed to use the old pointer because the provenance doesn't match.
Yeah. I may give an answer to him. Pointer plus 1 is still the end pointer of the variable x, and you're not allowed to dereference it.
Yeah.
Even though it points to y.
I get
the address
that,
is y. Sorry, the address is equal to y. It doesn't matter.
Yeah.
So does the transparent replacement mean the provenance stays the same?
Next slide. Yes.
So programmatically query the provenance?
No, you cannot programmatically query the provenance because the provenance is in the abstract machine together with the time travel and stuff like that. It's not on the CPU. Right? So
it's something that exists in the mind of the compiler.
Yeah. Well, the mind of the guy who wrote the optimizer in the compiler. Yeah. So this is undefined behavior because the provenance mismatch. And to fix it, we can use launder. Because launder essentially updates the provenance to make it correct. Right? You don't change the address, you just magically do the provenance is now whatever the address points to. So to answer the previous question, if you laundered pointer plus 1, I think it would be fine. Because now you've got a pointer of y.
But for launder to work, it has to be like fundamentally correct,
no, right? No, it cannot be fine because you're still doing the thing. Yeah.
But if you go to the last slide.
Yes. Yeah, I just realized that as well. Yes.
If you Oh well, never mind. You're returning y. Right?
Yeah.
Never mind.
Yeah. And launder. So actually, I think launder should make the dereference fine, but the compiler is still allowed to do the optimization because
you can't dereference the one past the end
yeah. This might be a different rule than that also applies here.
So does launder, if you launder pointer plus 1, is it still the end pointer of x, or is it the pointer to y which gets laundered?
It's still the end pointer.
Yeah,
it doesn't change.
It's still, yes. It's still the endpoint. It doesn't help in this situation, but it helps in this situation. In this situation, because pointer is not an endpointer and it points to the valid. Yes.
So, correct me if I'm wrong. My understanding of launder was that it is to let you point to a different type of object that was there, but it is not.
I'm gonna talk about that later.
But no, let me finish. But it was not a way to get rid of provenance issues, like. These are different things.
I don't think the original launder wording didn't say much about provenance.
Yeah, I mean the standard doesn't mention provenance, right?
Nobody in core can really agree what launder really means. Still to this day.
Yeah. And like provenance isn't a term from the standard. Provenance is a term compiler optimizers use. So I'm just using it because, like, to explain what launder does.
Pointer, I think, was the term in the standard, or used to be.
Sorry, what?
Safely derived pointer.
Yeah. Like I didn't put the wording anymore on the slides because the wording got really, really complicated, right? So now I don't know the details on the top of my head either. So a similar thing happens here with references, because references also have provenance, and then launder fixes the provenance.
That's really good.
Okay.
With the use case.
What?
I have a question, but maybe at the end.
Okay, sure. So every object has unique provenances. All objects in an array sort of have the same provenance, so you can use pointer arithmetic to get from one to the other. And when you reuse the memory of an object, this changes the provenance unless you're doing transparent replacement. But if you're doing transparent replacement, same provenance, you can continue to use it. Everything works fine. Yes.
So if you have multi-dimensional arrays, they all inherit the provenance of the top-level complete array because the constituent arrays have the same provenance.
Yeah.
And so on.
So the elements of a vector have different provenance. Because your each time you say
no, because internally, because the compiler allocates
object in there.
But the library will allocate a block of memory and put a sequence of elements. Yeah. It's not an array.
Yeah.
Right.
So
there is a lot of wording in the standard related to pointer arithmetic that is a bit buggy. I'm not entirely sure whether this applies to this vector. This is an incomplete guide. Yes.
Just a clarification, because it's kind of becoming a knot in my mind.
Okay.
You said earlier that you were talking about the abstract machine that's defined on the standard.
Yeah.
But now you said that provenance is not on the standard.
Yeah. So provenance is not a phrase the standard uses. The term provenance, it does not appear in the standard. But it's a useful terminology our compiler optimizers use. So I'm putting it in here to explain more about like std launder, because like std launder is not a magic identity function. Like it updates the provenance, right? This is like it leaves the address unchanged, but it updates the provenance, and this is I think makes it clear. Then it just somehow makes it okay, right? Okay. That I had a couple slides ago. Yes.
So like earlier you were talking about how pointer is like a pair of address and provenance, right?
Logically.
But like if the whole like end of or like the +1 issue still doesn't work because it's like one past or whatever, then like the pointer is actually a little more than
no, I think it's just like the provenance sort of remembers that it's a plus end pointer also.
But if that's the case, then launder should update.
Yeah, there's some wording for launder, and the consequence of that wording is that if you've got like an end pointer, probably then you can't. You're not allowed to call launder on it.
Okay, so it's like a slightly restricted population update or something along those lines.
I think that for launder to work, there has to be a proper object.
Yeah.
Right. At the end pointer, there is no object. You can't no matter what you do.
But at the address there is.
At the end address there is.
I mean, in the example there was the next object that happened to be there. But like logically, it's still like the address, there are like two things there. Like
No, I
like,
understand, but what I'm saying is like the address is the physical
Yes.
trait. The
Yeah.
provenance is the logical trait.
Yes.
If launder updates the logical trait,
Yeah,
then it
so
doesn't
so
really matter that
yeah, there is some
logically
precondition
we're at
like
the end of
launder
the
only
object. There's
updates.
something there at that physical address.
I don't have the wording unfortunately, but launder only updates the provenance like if some conditions are met.
Okay.
Right. Yes.
So one of the preconditions on launder is that all bytes of the storage that would be reachable through whatever the results are reachable through the given pointer.
Yes.
So because you can't already do that,
Right.
that's why you can't.
Yeah. Thank you. Because you can't dereference the endpointer, no bytes are reachable from the endpointer, so provenance.
So it
Launder
basically
doesn't help you.
observes that the provenance is the same, even though it's kind of like it doesn't change the provenance. It just observes that actually these two provenances that I've been thinking about separately are actually the same thing.
Okay, but you can also view it that way.
Yeah.
If you like. Yes.
Yeah, just a question. Is there any way to make that function we're talking about non-UV?
Probably not, because compilers do the optimization. Right?
I think if you had passed like stood launder of n% x plus 1,
Yes.
then maybe that would have worked.
Yes.
The compiler
No, because no bytes are reachable. No bytes are reachable.
You're right.
Yeah.
Now the compiler is just going to load it out of
Yeah.
register and not notice that it has changed.
Yes, like the compiler sees why's address hasn't been taken, so it's not actually in memory. Like the if condition is never going to be true anyway, right?
If X and Y were in a struct.
Sorry, what?
If X and Y were in a struct.
No, because they're separate sub-objects, they're not in an array. Like if X and Y were in the same array, then the code would work.
So the real question here is, sorry, Marshall.
Yeah.
I was going to say, consider a possibility where you're on a machine where the natural alignment is bigger than int.
Right.
And so X and Y have space between them.
Like I think the reason for like it checks first if it's
My example checks that to make that more. Okay.
So I think the true illustrative question would be if you had an array of two arrays of one element. Can you take a pointer to the first, like to the one past the end element of the first subarray and observe that it has the same address as the first element of the second subarray? Can you do that dereference? And I'm not sure you can.
What's the amendment I should use if I don't want to answer a question? Okay.
Because that's
moving on.
Moving on to type panning. So strict aliasing rule. We've got an int. We've got a pointer to int. We do a reinterpret cast. This is actually fine. We dereference it. This is undefined behavior. Right? So like colloquially, we say like you can't reinterpret cast between unrelated types, but this isn't true. You can do that. What you can't do is when you access the stored object through a type that is not similar. Right? That is the undefined behavior. Like creating a pointers, we can do all the time, right? Because the type of a pointer or a reference, like it's only really relevant when we access it. Like it doesn't really matter otherwise. Like only when dereference does the type. Otherwise, it's just a fancy comment. Yes.
This is why I think it's kind of odd, though, that even forming a pointer past the end is undefined behavior. Because again, if you don't try to access it through that pointer,
No, like so you can form a pointer past the end, but the pointer arithmetic is not allowed to.
How would you form a pointer past the end without pointer?
You reinterpret cast you and pointer some numbers.
Oh, I see.
Right? Yeah.
I would disagree with this slightly.
Okay.
Because pointer arithmetic.
Right. Fair enough. Pointer arithmetic, yes. The multiply and pointer arithmetic also depends on the type of the pointer. Yes, good point. This is why I give it at CppNow now. So the standard says like that has to match the type of the object stored at that address, which means that we can do this. Like we've got our int, we placement new a float at that, we can use it as a float. But we can no longer use it as an int, because we don't have an int. This doesn't violate strict aliasing, because we've got an object when we dereference it. Like, it's only about accessing a pointer when we don't have an object of that matching type at that address. Similarly, we could do that. This now does actual type panning. Like, sort of, because like we change creating a new object, so the values don't really, right? The values might get changed by this. Yes.
What happens like when the scope is exited? Like, is the int destroyed or is the float destroyed? Or
Because an int doesn't have a destructor.
Yeah.
When the scope exits, no destructor is called. The storage allocated by the declaration is deallocated, and this implicitly ends the lifetime of whatever object is in that storage based on the wording that I've shown earlier. Now, when you do that, you have to be really careful about how you got that pointer. Right? We got an int. We take that address, we interpret it as a pointer to float. This is fine. We create an int that object. We're not allowed to dereference the float pointer. Like, even though the pointer points to the correct address, has the correct type, and we actually have the thing that is there in there, like, it's the different provenance again, right? And it doesn't matter if we do it that way, right? F pointer points to an int, but we don't have an int. Right, so we either have to use like the resulting pointer directly, or we launder it to get the correct provenance. Yes?
What if I want to write that into a file or something and transform that into a character array to write that? Is that undefined behavior?
So
characters are special.
Characters are special.
Yeah. So what exactly? So you've got the int. You write the int to a file. You open the file. You read it as a float.
Yeah. No, I convert that int into a character.
Okay. I'll get to that. So this rule about how you got the pointer also applies to an unsigned char buffer. And this is why we needed that launder earlier. Because even though this implicitly creates an int for you, the reinterpret cast doesn't give you that int. Right? It gives you, it points to the char array and not the int that the compiler would really like to create in there. Right? And like, I consider this a bug. The author of P3006 considers it a bug because otherwise the wording like doesn't really make sense. Like there is some missing wording here to make this okay. Yes?
I'd like to add one thing, which is u in the pointer t has no provenance.
Yeah, yes.
Is that a pointer?
Yeah. I don't get into that in this talk. Yeah. Okay. So when you use launder, you use the storage of const heap objects, base classes, or non-unique address objects, or when you reuse memory as storage of a different type. So in other words, still never, but some terms and conditions may apply. So there is an exception for strict aliasing, two of them. First, we can interpret as the signed or unsigned type, and the second char unsigned chars.byte. So we've got an int, we interpret it as an unsigned. This is fine. I don't know why you would want to do that, but this works. Or you can interpret it as a byte. And the idea behind the last rule is that you can access the object representation, right? The sequence of bytes the object occupies, you want to print them, you can want to do something with them. Except this is actually undefined behavior, according to a bug in the standard. Because something got changed about the way the object representation is specified, we don't actually have an array to do pointer arithmetic with. And this got like changed accidentally in C++20 or something. There is another paper in flight to fix that as well. Because this should work. It's the same thing, like we don't have the object representation is a sequence of bytes and not an array of bytes, so we can't do pointer arithmetic. But this should work. So type panning in general, we want to interpret the bytes of an object of type T as an object of type 2. And actually my next slide is incorrect. So I'm just going to skip over that. Okay, so for example, you can do type panning via memcopy. This doesn't actually have anything to do with object lifetime. We've got an int, we've got a float, we memcopy them over. This just works, right? Because like we're just copying bytes, we have an existing int, we have an existing float, no object lifetime here. And also like no implicit object creation is going on. We're just doing a memcopy. The more modern version is bitcast, right? So you can bitcast it to float. This is fine.
But
yep.
So like that doesn't work though if you have like an arbitrary other type, right? It works between what it.
Oh yeah. So this entire section assumes int and float are the same size and alignment.
Yeah, but like let's say you have like I don't know, like my food type, which has the same size and alignment.
Yeah.
But it's not trivial, for example.
Oh yeah. Yes.
So like what are the requirements for this to work?
This is just like the precondition on memcopy is that it's like something trivially copyable or whatever. in order to call memcopy.
We should have just called it the concept memcopyable.
Yeah.
Does that take key? So
What?
memcopy takes like unsigned char, right?
Yeah.
Void
star. And then void star.
Void star. Okay, I thought it was. Okay,
And then internally it does magic, which isn't relevant, to copy the bytes over. Because as I said, like there is no because of the previous bug, they can't actually cast it to an unsigned char into pointer arithmetic legally, but you know.
Built-in memcopy.
Yeah, it doesn't matter how memcopy does it. Memcopy does it. Right. And like bitcast is like memcopy, but it's const_expr and it's nicer and but does the same thing. And again, no object lifetime because we create a second object by the memcopy. Another case of type pairing that works is here. So we've got an A with an int member. We create an A object. We get a pointer to we reinterpret cast the address of A to int and use it. This is fine. We can also cast it back and access the member directly. This is also fine. This is a special type panning exception because pointer interconvertible. If two objects are pointer interconvertible, then they have the same address, and you can use reinterpret cast to get an address from one to an address from the other, in this case between the first member of a struct and the parent. So they are interconvertible if they're the same, obviously. Union and non-static data member, and like standard layout class and the first non-static data member, and then strand stuff. So when we've got a pointer to the first member, we can reinterpret cast to a pointer to the struct it contains in and use it as if it were a struct, and vice versa. Yeah?
Like maybe there is, I didn't read the second half, but like from the first half, like it looks like I can just also have it in and convert it to a pointer to I can't do that, right? Like,
no, this is a dynamic property.
Oh, they're the same object. Okay.
Yeah. Yeah. This has to be like the sub-object dynamically. You can't convert an arbitrary.
I just read the first time. Yeah. The same address. Okay.
Yeah. If they are pointer and they're pointer interconvertible if. Right.
Sorry.
Yeah. And this is also, by the way, with the bug with the unsigned char and the stored launder, you would add like a clause here that an unsigned char array is pointer interconvertible to any objects implicitly created in that unsigned char array, and then the reinterpret cast works. But that wording is missing, so it's undefined behavior. So type panning via union does not work because finally we've reached the end of the sentence. An object is created when implicitly changing the active member of a union. Union int float, we create an int, we assign a float. This creates a new object at that place, the float, which is now okay, so we can no longer exit this as an int. Right? Type panning by union doesn't work. There is a sort of exception, the common initial sequence. So essentially, when you've got two structs in a union and they both start with the same members, it doesn't matter. So here we've got two structs, A and B. They both have an int prefix as the first member. And it doesn't matter whether we write u.a.prefix or u.b.prefix, both have the prefix. Right? So we are allowed to access them.
Thank you, Howard.
Yeah. This, however, doesn't have anything to do with lifetime. Essentially, the behavior is as if the corresponding member of T1 were nominated. So the compiler sees it, we access u.b.prefix. This is not fine, so the compiler updates it as if we had written u.a.prefix. And it does it like dynamically at runtime to always ensure that we're accessing it. But it doesn't have anything to do with lifetime, it just makes the access correct all the time.
Yeah.
Yes?
But it doesn't go for names, it's just the type list.
Yes, it's just the type list, yes. Yeah. They could have different names. And like there is some wording about like when exactly they're like the same initial sequence or whatever that you should read when you want to rely on that. Yeah. Okay. So let's end this with invalid and zombie pointers. So lifetime is important. What happens when we access it outside of lifetime? So before the lifetime has started or after it has ended, any pointer may be used only in limited ways. And similarly, any reference may only be used in limited ways. What are those limited ways? Well, what do you expect? Like we can freely take address and references, whatever, and we can compare the address of the thing. Like this is fine. Like we're not accessing the destroyed object, we're just creating references and pointers to it. But we cannot actually access it, right? Because we don't have an int object, we've destroyed it. So in general, we have undefined behavior if such a pointer is used to access the value of the object, to call a non-static member function, to delete the object because it's already destroyed, right? Or to do anything with virtual base classes or dynamic cast, because then you need to go into the v pointer, but which doesn't exist anymore because the object is destroyed. Yes?
I mean, it makes sense because you're not accessing the value, but it's explicitly called out that you can call static member functions on a destroyed object.
Yes.
Oh, okay.
Because they don't actually have
Yeah,
an
that
object.
makes sense. It's just kind of odd.
I don't know whether the grammar, like what happens when you write a dot non-static, how's that defined in the...
That's permitted.
Yeah, then that's permitted. But yes, it actually says non-static member function. Yeah.
Yeah, you could have something like a static member function recreate in place.
Yeah. 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 Okay, so the previous section, it has a caveat, like before the lifetime has started, but after the storage has been allocated and before the storage has been released. Because there's an additional caveat here if we access them in that case. So when we deallocate a region of storage, all pointers to those addresses become invalid pointer values. You're not allowed to dereference them, obviously, because we don't have any objects in there living by definition. We cannot deallocate them because the storage has been, but anything else has implementation-defined behavior. In particular,
passing as an argument.
Such as looking at the pointer in any way. Yeah. It has implementation-defined behavior. In particular, it can create faults. So what this means is we've got our int. So in this case, we've got an int, we get a pointer to it, we destroy the int, we dereference the pointer. This is obviously undefined behavior. But we're allowed to compare pointer to null pointer, right? Because it's just a pointer to x. However, if we put it on the heap and we delete it, this deallocates the storage. Dereference is still UB, but the comparison with null pointer is implementation defined. Because pointer points to deallocated storage. So it becomes an invalid pointer value, and all other operations are implementation defined. In particular, it might return true. Because an implementation might help you and say, okay, when you delete a pointer, we set it to null pointer. Or it can trap, or it can do like whatever implementation defined thing might happen. And this is really fun. So I'm taking an example from a proposal that wants to fix it. We've got a stack using atomics, right? A singly linked list. So we've got a push that takes a node, we load the current top, we set the next to the old top, and then we have a compare exchange weak loop and repeat that until we actually manage to succeed, right? And then we've got a pop all function that just sets top to null pointer and returns the old value to, and now the caller has the entire stack. This is a pretty standard atomic stack operation. So let's see what's going on here. Top points to node 1 at memory address A. Now that T1 starts, T1 allocates node 2 at a memory address B. It executes old top load and sets the next to old top. So now the pointer diagram looks like this. And because it's multi-threaded, now that T2 comes along, execute pop all and deletes node 1. This means that next and old top are now invalid pointer values because they point to deallocated storage. So when we do the compare exchange weak, that's implementation defined, which means it might trap, right? Which is obviously not bad, not great. But it gets even worse. So let's say we're in this situation. We've deleted node 1. Then we allocate node 3, which happens to reuse the memory address of A. And we successfully pushed that onto the stack, right? So node top and points to node 3, and old top points to the deallocated node 1, whose memory just happens to be reused. The compare exchange weak is implementation defined because like invalid pointer value. But this time the consequence is more subtle because let's say compare exchange weak in this case either has to return true or false or can trap. But what should it return? If the comparison returns 2, we've got like invalid provenance in the next pointer of node 2 because it points to the provenance of the deallocated object, right? So we can no longer use the stack because we just got a wrong pointer in the beginning. And like if it returns false, like it can't because we cannot compare the provenance, right? The hardware cannot do a compare exchange. We cannot look at the provenance. So like this is a bug in the C++ standard. There is no like this is just bad behavior in the like something should happen, but the standard says it's implementation defined what happens, and whatever actually happens is not great from the terms of the abstract machine. It obviously works on the CPU because the CPU doesn't care. Like this is all about the abstract machine. And so the proposed solution from the paper says, okay, comparison of invalid pointer values should be meaningful and not implementation defined and actually do what you sort of expect. And then we need to use some launder-like mechanism to update the provenance, but it has to be recursively update the provenance of every pointer reachable from the initial pointer to make the entire thing work. But this has some serious optimization implications. So there is, like, it's an open research problem in the C++ committee to make this well-formed. So with that, I've covered everything I wanted to cover in the incomplete guide to object lifetime. I will end with some personal guidelines. Don't rely on implicit object creation. Like, it's really an escape hatch to make C-like code work. It's much nicer if you explicitly call start lifetime as, right? Makes it more obvious what's going on. Yeah, like placement new to explicitly create a new object, start lifetime as to, like, you've got some bytes, you want to start using them as an object without changing the values. Whenever possible, use the pointer from placement new and start lifetime as directly, right? Then you don't have to worry about any launder, because you're just already using the valid pointer with the valid provenance. And finally, like, don't use unsigned char buffers to, like, do deferred construction. Then you get into weird, like, annoyances with reinterpret cast. Use the union of, like, char empty and the type T. Like, this also constacks in some situations. Like, this is much nicer. You don't have to worry about any of the consequences. And with that, I'm done. So I work at ThinkCell. We're hiring. So if you want to work with us, I've got a bunch of socks. So if you haven't gotten any of the ThinkCell socks, you can pick them up here. They're L value, R value socks. Okay. I may or may not answer your questions, but you can feel to ask them.
Yeah. So one of the problems with the union storage trick is that you can't use magic values inside, like, or in the object prefix as signifiers.
Right.
So it's not, you can't implement an optimized optional that uses tombstones and stuff like that.
But, like, if you've got, like, tombstones, then, like, the tombstones give you a T anyway, right?
No, the tombstone just tells you if it's there.
Yeah, but, like, you can frame that in terms of
you can't read a partial object because it's not an array.
Yeah.
So if you have an array, then you can then copy part of the array, and that's fine.
Yes. Well, sort of, like, because of the bug in the standard, once you put something in the byte buffer, you don't have an array anymore. So you can't do pointer arithmetic anymore because you don't have the array. You should be able to do that because it's the object representation, but there's a bug. But
it's terribly fun to compare vtables to, like, vtable pointers to nil.
Yeah.
It's really efficient.
Yes.
I just wanted to say I really enjoyed this, and I also wanted to give you credit for being willing to give a talk like this. It's C++ now. It takes a lot of confidence.
I unfortunately already gave the talk at ACCU, which was bad timing, but I'm going to give it again. So.
I want to congratulate you on your level of preparation.
Thanks.
What about this? Next slide.
Timing too. It's like, next slide, not later.
If I have a pointer to some object inside an enumeration, a struct, not the first one, but something, and the offset of that, can I recreate the pointer for the struct? Is that legal?
No, because you cannot do pointer arithmetic. Right? Yeah.
Similar question. Say you have struct int AB. I have a pointer to A.
Yeah.
I can convert that into a pointer to struct.
Yeah.
And then go modify B.
Yes.
And that's fine.
That's fine. But you cannot go from pointer to B the other way around.
Zig has a feature like that.
Yes.
You can launder your way around. Right?
Yeah. So to expand on your answer. So you've got struct int AB. You take the address of B. You cannot get to the rest of the members because that would do, like, pointer arithmetic outside the thing. But when you got the address to A, you can convert that to a pointer to struct, and then you can access B. Or alternatively, you can access, like, the object representation, assuming that becomes legal again, and then use offset off to get B. But you cannot go from the object representation of B, like, to the object representation of the struct because it's like a sub thing, and you're not allowed to go out of bounds of that, right?
Go fast. So now if I have the same thing, but I do it using multiple inheritance, Then I can absolutely cast my pointer to base into a pointer to the right that has both things. And then go back to the other base, and that's fine.
Yes, because it's different rules. Because then you're doing like a static cast, not a reinterpret cast.
But it's the same machine stuff.
Oh yeah, like none of the this is we're in the magic land where we do time travel.
So one guideline I might add here, I think, is to be extremely careful with your usage of no unique address, because it turns a lot of these things which are only in the abstract machine, it turns them into actual bugs in your code, like it's actually going to break. So you have to be really careful if you intend. I mean, you must always sort of intend that your type might be used as a with a no unique address attribute. So whenever you're doing things like placement newing inside, like if you have an object inside your class and you're placement newing it, like you're implementing like a stood optional or something like that, right? You have to be really careful, because if from the outside it gets used with a no unique address, this might actually cause problems, right? So for example, something we do in libc++ since recently, because we had issues like that in some of our view adapters, in some of our ranges views, we actually ensure that we do not leave any trailing padding at the end of the object, and we actually have to do work for that. Like we prevent our class from having any trailing padding, because if we happen to be used with a new unique address, the stuff that we're doing inside the implementation of the class would be overwriting the user object that was hidden in our trailing padding. So essentially, the lesson here is you do not own your padding bytes anymore, because no unique address exists, and this will actually break you. Like we had a very small ABI break in libc++ because of that. It took like a huge amount of work to actually make
like the example I showed with the assignment where you destroy it and placement new. This will overwrite the padding bytes, and you don't, the compiler might have put something in there, which is why there was this caveat about transparently replaceable and no unique address. Right?
So if you do that or that sort of stuff, then you need to at least make sure that there are never any padding bytes at the end of your object. That way you truly own all of your, basically that way it's impossible that you're going to be overlapping with another object.
Is std launder defined to be no op?
Std launder is __ built-in launder.
Right, but does the standard put any restriction? Can it execute code?
I think the standard just says something. It takes a pointer to some bytes reachable and returns a pointer to the same address but different object. Right. I mean, I don't know, but an implementation is allowed to do
I think we would be allowed to do that, but it's just
So I'm wondering, the memory tagging stuff. How does launder work?
It doesn't do anything special.
But then, isn't it supposed to work then? You can.
Yeah.
Memory tagging is just like a way to find out when you actually misuse something. It doesn't allow you to it doesn't change what the valid semantics are in the program.
Yeah, and
so the tagging then doesn't correspond to the provenance. My model was that tag was kind of an approximation of the provenance, but it's not.
It's some sort of provenance, tracked in the hardware, but not the same provenance that we're in this magical wonderland talking about.
Sorry, it's way closer.
Yeah,
like 16.
And std launder is just there for the optimizer too. People want to eat lunch, so let's just end it here. And I've got the socks.
Actually, there's something else in this.